squared, or cosine squared is 1 minus sine squared. So these are really just two formulas here, but written in many different ways. Questions?
Is this where it goes crazy?
Yeah. Yeah. Integration by parts isn't going to work. Integration by parts is kind of set up for when there's a transcendental in there. You know what, though? 1 minus x squared. Doesn't that look a little bit like that? What if I replaced x with sine theta? This is called a trigonometric substitution. So it's not a trig integral. Notice we aren't starting with trigonometry in the integral. But I am imposing trigonometry on this in order to get rid of that 1 minus x squared. I mean, after all, if I change that to 1 minus sine squared, what is 1 minus sine squared? Cosine squared. What's cosine squared to the 3/2 power? Cosine cubed. Cosine cubed in the denominator, that's a secant cubed in the numerator. Let's see what happens here. What's dx? Cosine theta, d theta. So now let's do the substitution. Dx becomes cosine theta d theta. The denominator is 1 minus sine squared theta to the 3/2. But 1 minus sine squared is, as we already said. So I get integral cosine theta d theta over cosine squared theta to the 3/2. So that's the integral of cosine theta d theta over cosine cubed theta, which is integral of d theta over cosine squared theta. And 1 over the cosine is secant, so 1 over cosine squared is secant squared. So this is really the integral of secant squared theta d theta, which is tan theta plus an arbitrary constant. The only thing is we have to go back to the original variable. So how do I go back to x's? Remember, my substitution is x equals sine theta. So if theta is the angle, sine is opposite over hypotenuse. Using Pythagorean's theorem, the third side is square root 1 minus x squared. So I can now tell you the tangent is this over this. And so final answer, I get x over square root 1 minus x squared plus an arbitrary constant. And you did your first trig substitution. Gosh, that was fun. Shall we do another one? Yes. Well, really, that's pretty much the whole lecture on 7.3. All things trig here. How about if we try number 22 on page 531? So the three basic trig structures that you're hoping to mimic here are these. Usually we write cosine squared is 1 minus sine squared. Secant squared is 1 plus tan squared. And tan squared is secant squared minus 1. So typically, we're going to use these three trig formulas in three very related but slightly different situations. Here, this is the substitution you think of when you get a squared minus x squared. Right, because it may not be a 1, it may be some other number. We can change that number into a 1 by factoring out an a squared. So if I get number minus variable squared, I think of this one. If I get number plus variable squared, I use this substitution. And if I get variable squared minus number, I use the third one. So number 20 is the one I asked you. 22. Somebody read 22 to me. Integral. What are there limits of integration? I don't remember. I can walk back over here and look myself. I do not want to do it. Just 0 to 1. That was difficult to read, was it not? 0 to 1, square root x squared plus 1 dx. So I see which one of these has x squared plus some number.
1 plus 10 squared.
Right there. So I'm going to let x equal to secant. Excuse me, x equal tangent. Right? So I'm trying to get this. If I have 1 plus tan squared, that'll become a secant squared, and under the square root, that simplifies nicely. What is dx?
Secant squared.
Secant squared theta d theta. Okay. So, oh my goodness, new limits of integration. When x is 0, well, the tangent of 0 is 0. So when x is 0, theta is 0. Well, what about 1? The tangent of pi over 4 is 1. So when x is 1, theta is pi over 4. Square root. X is tangent, so tan squared theta plus 1. Dx is secant squared theta d theta. Well, that's the integral from 0 to pi over 4. That's going to be secant cubed theta d theta. I didn't have to worry about absolute values here. I guess I skipped a bunch of steps on you. Let me go back and put them in. I saw those looks. That was the square root of secant squared theta times secant squared theta d theta. Normally, I would say absolute value of the secant. But the secant is positive on 0 to pi over 4, so that is not necessary. This is now the integral 0 to pi over 4 secant cubed theta d theta. So why did I pick this particular example? Well, not only to do a slightly different substitution than what I invented here, but also to come up with this. Because I'm kind of promising you guys that I'm not going to expect you to integrate odd powers of the secant. Does anybody remember what I have to do here? Integration by parts. And I end up having to add a secant cube back over to the other side. It was not a pretty situation. Do you remember what the actual integral is? I don't either, because it's too long and involved. So on this one, this is one where if you look back at those tables, I would provide a table entry for secant to the n theta d theta, and you would use that table entry now to finish this up. So let's do that. Look up in the table, what is the formula for secant? I'm going to have more room here. So this is a kind of 7.8. We're sort of doing that out of order now. You're getting a preview of it. Tell me, what is the formula for the integral of secant to the n theta d theta?
Be 1 over n minus 1.
1 over n minus 1.
Tangent theta.
Tan theta.
Secant to the n minus 2.
N minus 2 theta.
Times u. to be plus
Plus an integral now.
to be plus n minus 2 over
Go on.
over n
n
minus 1.
N minus 1.
The integral
Integral
of secant,
n minus 2.
so n minus 2, yeah.
Theta d
Yeah.
theta.
That's what I thought.
They actually have it like as a full answer.
I understand it, but what I'm trying to do is teach you
Yeah.
to use this formula. All right, this is called a reduction formula. So it works with any power of n. What's our power of n? 3. So every place you see an n here, now write a 3. So I've got 1 over 3 minus 1, 1/2, tan theta, secant to the 1, so secant theta, plus, remember, n is a 3, so 1/2 the integral of secant theta d theta. And all this is evaluated 0 to pi over 4. So here, hopefully you have committed that one to memory, right? I won't provide you with that one. Somebody tell me what is the, well, let me write this down. 1/2 tan theta secant theta plus 1/2 an integral of the secant, ln absolute value, secant theta plus tan theta, and now remember this is all evaluated 0 to pi over 4. Well, we didn't need the absolute values because
It's from 0 to 5.
secant and tan are both positive on 0 to pi over 4. But now I can plug in pi over 4. So the tangent of pi over 4 is 1. The secant of pi over 4 is rad 2. Cosine of pi over 4 is rad 2 over 2.
Okay.
Right, and rad 2 over 2, remember that was really this.
Right.
So if you're doing the reciprocal, it's easier to use this instead of that. Plus 1/2 ln, and I guess I'm gonna add these, so 1 plus rad 2. And you're done. You don't have to give me a decimal, you can stop there. So somebody look at the assignment and show me an even number problem where we would, notice we did one substitution where we let u equal the sine. We've now done one where u is equal to the tangent. Find one for me where I'm gonna let u equal the secant. An even number problem. Well, 24, that's not a number minus something squared. I think a more slight, what about 16?
Yeah.
Let's do 16.
Alright, I have one question regarding
Which
22.
Sure.
What happened, you got second to the power of 3 theta. How did you do that?
It's from the black.
Well, the square root of secant squared is secant.
Oh, okay, got it.
So secant to the 1 times secant squared.
Thank you.
Sure. So what number did I say, 16? So somebody read 16.
It's integration from the 2 over 3 to square root of the limits.
Okay, then limit square root of 2 over 3.
Oh, okay, forget the limits of integration for now. It's the technique I'm trying to exhibit here. dx over?
X to the 5th, square root of 9x squared minus 1.
Okay, so I am going to let 3x, well, let me rewrite this for you once. I don't want 9x squared minus 1. I want secant squared theta minus 1. So I'm going to let 3x equal secant theta. That will now be secant squared theta minus 1. Secant squared theta minus 1 is tan squared. Square root of tan squared is tangent. I will get rid of the radical by doing this. By the way, 3dx is secant theta tan theta d theta, or dx is 1/3 secant theta tan theta d theta. I need all of that to substitute for the numerator, don't I? So let's perform that substitution. Dx, as we just wrote, is 1/3 secant theta tan theta d theta. The denominator, well, x to the 5th is secant theta over 3 to the 5th. And now I've got under the radical square root secant squared theta minus 1. Doesn't this look like a pleasant little problem? So I guess that's going to end up being a 3 to the 4th. Oh, how did that happen? Well, there's a 3 to the 5th. All right, I'm dividing by a 1/3 to the 5th. So that's a 3 to the 5th on top. There's a 3 on bottom. Never mind. Let's write that as 1/3. So much. Here, if you take 1/3 and divide it by 1/3 to the 5th, that's what I'm doing, aren't I? Here's a 1/3. Here's a 1/3 to the 5th. That 1/3 to the 5th is in the bottom. I'm dividing it according to that fraction bar. So that's 1/3 times 3 over 1 to the 5. That's 3 to the 4th. This is 81.
How did you get 3 to 4?
Oh,
Sweet. Okay.
don't really hit him, I like him. Secant theta tan theta d theta. Secant to the 5th. Square root of tan squared theta. Now, normally we would have to worry about absolute values. That's why they put the limits of integration on there so you don't. So we're just going to blow that off for now. And this is 81 integrals d theta over secant to the 4th. After all, the tangents here cancel. Secant to the 1, secant to the 5th, secant to the 4th. Secant to the 4th is cosine to the 4th in the numerator. Secant to the 4th in the denominator is cosine to the 4th in the numerator. And we know how to solve that, hopefully. That is 81 integrals cosine squared squared. And we're going to rewrite cosine squared as 1 plus cosine 2 theta over 2. And I'm just going to put a dot, 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 because hopefully you can finish that now. So those are the horrors that you're up against in 7.3.
How do you know they change it to the cosine?
Pardon me?
How do you know they change it to the cosine with the 2?
Because I'll do anything to get rid of secant.
Okay.
Secant suck. So, 7.1. Oh, not 7.1, is it 7.4?
Yeah, three.
Three? Yeah, 3, 7.3. So 7.3, let's see, 1 through 6,000.
The even.
1 through 29 the odd. I'll have a little bit of mercy and not give you 31.
Thank you.
Oh, don't worry, that mercy will be short-lived. Oh shoot, that's an even, huh? Oh, I don't want to do that to you. Let's do 37. Oh, stop that. Do I really wanna do that to you? Yeah, oh, yeah, 37 and 41, no, we have to do 41. 41 is one that we had to pull a trick to do in Calc 1. You did number 41 two ways, you used both the shell and the disc and washer method. But in order to do that, you had to interpret the integral, but you had to solve the integral by interpreting it in terms of areas. We don't need to do that no more. Now we know how to do trig substitutions. We'll be able to find the volume of a donut, a torus that is, directly, not with the tricks that we had to use in the previous class. So there, that will make your life miserable tonight.
And there's more.
Oh yeah.
There's more.
Now we're gonna do 7.4. Have any of you guys ever heard of partial fraction decomposition?
Yeah.
You have all supposedly heard of it, and you are all responsible to already know how it works. I have not enough time here to go over the whole thing.
Which one is it?